Perfect. All right. So hello, everybody. Welcome to the 1W-MINDS seminar. We are delighted to have Rocio Diaz Martin here from Vanderbilt University, where she is currently sitting next to a nice sunny window to talk to you about applications of optimal transport. So I will turn things over to you now, Rocio.
Thank you, Mark, very much for this opportunity and for make me feel more relaxed. Today I'm going to present some new stuff that we've been working since I came here to Vanderbilt as a postdoc, which has to do with applications of optimal transport. And I'm going to mention works from other researchers. Some of them are my collaborators, because this is like an area that I was introduced by Gustavo Rode and Sohail Kolouri, and well, my main mentor has been is Akram Al-Rubi, and then other collaborators that have been here at Vanderbilt, Yikun, Ivan, Sumati, and other grad students from the MINT lab. So, okay, let's start. The optimal transport problem is itself a problem from applied math, but we are going to use like byproduct from the setup in order to after I set up the problem, I'm going to have some byproduct to do other applications. But at the very beginning, I'm going to be a little bit basic and introduce the transport problem, the optimal transport problem. So starting from a very vague perspective, the task is that we are given two configurations of masses, and we have to move one configuration into the other configuration. And in that process, we have to optimize a specific cost. So this is kind of a matching problem. And I have to formalize what I mean about configuration of masses. In our case, these are going to be two probability distributions. And I have to introduce what I mean about moving one into the other, in which sense I refer to that. So I'm going to introduce different formulations of the optimal transport problem. And the cost is going to be a functional that has to do with a distance or an energy. So the first formulation that I would like to introduce is from a static point of view, by Kantorovich. So suppose we have resources represented by this discrete measure mu, and a demand represented by this discrete measure nu. I don't know if you see my cursor, but yeah. And as you see here, both of them are probability measures. So they have the same total mass. And we have to distribute the resources to the demand. Okay, so let's put an example. So mu is represented by this discrete measure here, that at location 1 we have 1/2 of mass, and at locations 2 and 3 1/4, and nu is represented by this uniform, let's say, distribution with masses located at 1, 2, and 3. So if we have to distribute our resources to our demand, what we have to do is a table that we are going to call a plan, and say, okay, the mass that I have at location 1, I'm going to put 1/2 in location 1 of nu, and 1/4 at location 2. And the mass that I have here, I'm going to send it to location 3, and that is what I have here in my table. And the last quarter, I'm going to send it to location 4 in my demand or target. So this is a pretty simple way of setting up how to distribute, and then we want to minimize, because we can fill in this table in different ways. So we are going to pick the plan that is optimal in a certain sense. So which is our minimization problem, is the following. I want to minimize over all the possible plans that I'm calling pi here, that are nothing but the tables that I had before, or matrices. And these should be probability distributions in the product space, and they have to have marginals mu and nu, because they come from a table, as I showed before. And we have to minimize the distance of putting mass that was in location xi to location yj. And the mass that I'm carrying from xi to yj is exactly the box that I had in my table. And this is nothing but a linear programming if we have to solve it. Okay, so in the case we had before, the cost, we can compute it as follows. First, we have to match 1/4 of the mass that I have here to 1, and since we are not moving, we have 0 there. Then I'm going to take the remaining quarter that I have here to location 1, to location 2, sorry. So the distance that I'm walking is 1, and I have to square it, times the mass that I'm moving, 1/4. Then the quarter that I have here, I'm going to move to 3, so I have the same computation there, and the quarter that I have here at 3, I'm going to move to 4. So this is the mass that I'm carrying, and this is the square distance that I'm walking. So the total cost is 3/4. Okay, we could have another plan. Let's say now I don't want to move that much. I'm going to leave the mass that is here at location 2. I'm going to leave the mass that is 3 in location 3, and then I'm going to fill the 1 and the 4th location with the big mass that I have here. So I fill the table this way, and notice that the only time that I'm walking is when I carry 1/4 to 4, and in that case I'm carrying 1/4, and I'm walking 4 minus 1, so 3 steps square, and it gives me a higher cost. So I have to pick the one that is minimal, the table that is minimal. Okay. And it happens that the one that is going to be minimal is the table that will have the minimal cost, is the one whose that resembles the graph of a function. The optimal plans are not going to be unique necessarily, but we will have a plan such that its table resembles the graph of a function. So if it is the graph of a function, then there is no mass splitting. And we are going to be interested in those cases when there is no mass splitting when carrying mass from one distribution to another. Okay, so this gives me the chance to talk about the Monge formulation. So here, instead of tables, I want to match one distribution that I'm going to call reference to the target through a function, a measurable function t. So I want my target measure to be the push forward of the reference measures. And among all the possible maps t that I'm going to call Monge maps, I want to pick the one that minimizes the distance in the following sense. Among all the possible measurable functions t that pushes mu to nu, I want to pick the one that minimizes this functional. If I'm carrying mass from x to t of x, I'm carrying mu of x mass, and I want to minimize this quantity for all x. And so I have to sum all the x's. This minimization problem will be a minimum. In principle, it's an infimum, but it's going to be a minimum if there is no mass splitting in the process. And you can think of this in terms of measures. I like thinking about the problem that way, but you can think of this problem in terms of random variables, or in case your measures have densities, you can also think of this problem with densities. My notation is going to be, in case mu has a density, its density is going to be called f sub mu, and the same for nu. Its density, in case it exists, is going to be f of mu. So in terms of random variables, if you start with a random variable x, you want to end with y, that is t of x. That's the formulation for random variables. And for densities, in case you have them, you use the change of variables formula. And I like to recall this formula, because here we see that this formulation of finding a t such that matches mu and nu, with this formulation is a non-linear formulation, which is very different from before, that Kantorovich formulation was linear. Okay. And this non-linear constraint has to do with the conservation of mass. I'm matching the full mu to nu. And okay, in case the map T is the gradient of a convex function, then the box equation that I have on top is exactly the Monge-Ampere equation. And this condition of having T being the gradient of a function, of a convex function phi, is not super restrictive, and indeed we will have the following theorem. So first of all, if my starting measure, the one that I call the reference measure, is absolutely continuous with respect to the Lebesgue measure, so I have a density, then we are going to be in a scenario where we can afford not mass splitting, and there is going to exist one and only one optimal Monge map to any target nu. The Monge map will vary from target to target, but if I fix a target, I will have one and only one optimal map. And Brenner's theorem tells us that unique map is going to be the gradient of a convex function. And in the case of being in one dimension, that unique Monge map is increasing or monotone function. Okay. So by knowing this, in 1D, we are going to be able to have a closed formula for this unique Monge map. So on top, I put the characterization of a map, just a map that pushes mu to nu in the case of having density. So on top, I have the change of variables. And notice that I started here accumulating mass. So here I have my cumulative distribution function that I'm going to call with the capital F. So this is the cumulative distribution function of the referent until x naught. So this area here. By setting this integral different, so changing the limit here, I have here the cumulative distribution function at t of x naught. So all this area that I have here. So notice that here we have the conservation of mass. All the mass that I have here should be equal to the mass that I have here. And since these two quantities should be equal, we can solve for t. So t is going to be the composition of these two cumulative distribution functions, where here I have the inverse which is the quantile function in this case. It's not a usual inverse, but it's a quantile function. And these compositions, since cumulative distribution functions are increasing, the quantile function is going to be increasing as well. So this composition will be an increasing function. So this map should be the optimal because of the previous theorem. And we have a closed formula for the optimal map. Okay, so this has been like a brief introduction of the first two formulations of the optimal transport problem. Please feel free to interrupt me at any time. And I want to say something else before I move to the first byproduct that I have. The Brenier theorem that I introduced before only works for cost functions that are strictly convex functions. If I change my cost function to, for instance, just the absolute value or the L1 norm, not the L2 norm, then we could have not uniqueness of our Monge map. And a very illustrating example is the one of book shifting. Suppose I have a shelf of n books and I have an empty space here. And I want to fill this gap and have a empty space here on the other side. If my cost function inside the integral is this one, then I have two functions that are optimal for this one. The first one is, okay, push all the books one unit and fill that gap that way. And the other way is pick the last book that I have here and bring it here by, so you are going to move this last book n units here. So the cost is going to be n and n in both cases. So I have not uniqueness of my map. If I want uniqueness, the Brenier theorem holds when I have a strictly convex cost function, x minus y to the p with p greater than 1, or the p equals 2. So for the rest of the talk, I'm going to just pick p equals 2 because I want uniqueness. And in that case, the best map is the one that has to do with pushing all the books small units and not the one that is, okay, pick one and move it a big gap to the other side. Okay, so the first byproduct that I want to introduce is interpolation based on optimal transport. So the cartoon picture that I have on top has to do with what I call linear interpolation. So if I have two measures, mu and nu, the blue ones, and I want to move this from this side to the other side by interpolating, so I have an interpolation problem. Suppose these two have densities as in the figure, so I can do the easier line in the density space and just match them with this convex combination. But also and notice that here what happens in an intermediate step is that I'm going to contract the mountain that I have here, mu, and it's going to be appear another mountain here until this process ends in nu. So this interpolation is not transport-like. If I do an optimal another interpolation with optimal transport, suppose T is the map, the Monge map that I introduced before, that matches mu with nu, and I do this interpolation. So the interpolation here is between the identity and T in the space of functions, and then I push forward the reference to the target. So notice here, if when t is 1, when t is 0, let's start with 0. When t is 0, I have here the identity, so I'm started at mu. And when t is 1, this disappears, and I have just t push forward nu, and that was the property of t, that t was pushing mu to nu. And in the intermediate steps, I have things like the red one. So you are going to effectively transport mu to nu in the intermediate step as well. And so in both cases, I have curves of measures, and the second one is more transport-like and has to do with a geodesic interpolation in the sense that I'm going to introduce now. So I have.
So there's a question in the chat with, I think,
yes.
PDE type reference.
Okay. Does the interpolation solution minimize the sum of the value? Yes, exactly. That has to do with the thing that I'm going to introduce now. And please, if I'm not answering the question with this, ask me again. So the two formulations that I presented before, Monge and Kantorovich, are static formulations. But now we are going to introduce time, and I'm going to talk about a dynamic approach of optimal transport. So suppose my two distributions, mu and nu, are represented here as heat maps, and I want to be at time 0 with mu, and I want to end at time 1 with this other distribution. And I want to do that by defining a curve of measures that I'm going to call rho of t. Rho at 0 should be nu, rho at 1 should be nu, and this curve is going to have a velocity, and by setting the conservation of mass, that everything that is carrying out should be carrying in, the equality, and which is this what I have here, and then using divergence theorem, we end up with the so-called continuity equation plus the boundary, the not boundary condition, the initial condition, initial and final condition in time. So this continuity equation has to do with this property of conservation of mass. And then among all the possible curves and velocities, I have to pick the pair that optimizes, sorry, I have to go the other way, that optimizes the kinetic energy. So among all the possible curves of measures, rho having velocity vt, I want to pick the one that minimizes the kinetic energy. And this rho v should satisfy the continuity equation that I have here. And it happens that when having a Monge map, the curve rho t that optimizes this kinetic energy is given by the interpolation that I showed before, and the velocity is constant. And this kinetic energy, something else that I have to say is that represents also the length of the curve. So that's why I have a geodesic interpolation if I pick exactly this curve. So with these three ways of setting the optimal transport problem, once we achieve the minimum, once we optimize that, we get what is called the Wasserstein distance, or the earth movers distance. So the formulation that I have in the first line is by Kantorovich, the second is Monge, and the last one is dynamic formulation. The conditions that I have here, the subject 2, are the preservation of mass. So the preservation of mass condition is that T should be a push forward, should push forward the reference to the target. Here that the curve of measures and the velocity should satisfy the continuity equation. And for Kantorovich, that the plan, my tables, my matrices should have marginals mu and nu, and the cost functional that I have to minimize. So with this Wasserstein distance, I can end up my space of probability measures. I put the two because usually we use probability measure with second moment finite so that this expression makes sense. But if you pick omega to be compact, you don't need to add this hypothesis. So with this distance, I have my probability space that can be viewed as a metric space with this distance. But also it is a geodesic space. Given any two measures, I have a curve of measures that minimizes this distance with the geometric approach. And moreover, it is a Riemannian manifold. So I can see this as a manifold, and the tangent space has an inner product. So that last part that I didn't talk before is the one that is going to allow us to introduce our tools. So we can view the space of probability measures as a manifold, the one that I have on top. And if we pick one measure, there we have our tangent space. And the tangent space results of being nothing but an L2. And it's the L2 of all the velocities that I have from the dynamic formulation, all the velocity vector fields. That should be finite with the 2 norm. So we are going to use the tangent space for our representations of measures or signals or data or densities. So in the Wasserstein in manifold or in the space of probability measures, we measure distances with the Wasserstein distance. And I want to use the tangent space to measure distances in the tangent space, and this distance be similar with the Wasserstein distance that I have on my manifold. So I want to introduce the tool that we have been using, which is the linear optimal transport transform. So it's a transport embedding made out of optimal transport. So the recipe is the following. You fix a referent mu. You are in your Riemannian manifold, the space of probabilities with the Wasserstein distance. So you have a tangent space at your reference measure mu given by an L2 space. And you are going to map other target distribution to the, I'm going to name this application with hat because it's going to be a transform. So we use the notation of Fourier, let's say. And this hat is defined by being the velocity, the optimal velocity from the dynamical formulation. And I said that velocity is constant and is given exactly by the optimal Monge map from reference to target minus the identity. So equivalently, we could define our map, our transform, as just the Monge map, the optimal Monge map, just by subtracting the identity. So notice that this is different from Fourier in the sense that this is a non-linear transform. The map carries a non-linear condition, as I mentioned before. And so with this application, we can set up what we call the linear optimal transport distance between two target measures, nu1 and nu2, and we just compute here the L2 norm in the tangent space, that is an L2, with weight the reference of the two embedded signals. And so this is nothing but the distance between the two velocity vector fields, or the distance between the two Monge maps, optimal Monge map. Both optimal Monge map, notice that start at the same reference and end at the given measures nu1, nu2. And not only that, we have a way of inverting this application, this embedding, this transform, in the following sense by using Brenner's theorem. When we have here a function that is the gradient of a little function, then we just do the push forward to obtain a measure here. We do the push forward with the fixed reference here. So this tool takes measures to functions, and the thing that is fixed is the reference measure that we choose that one. So in the image that I had before, the distances in blue, I'm going to pick mu to be the reference, so I'm going to take the tangent space at that measure mu. So that will be my zero in the vector space, in the tangent space, and the distances here in blue are going to coincide with the distances with the corresponding transform measures. So the LOT distance from the reference to any target is exactly the Wasserstein distance, because the reference is zero. So here we have nothing but the Wasserstein distance. But now we can approximate these other distances, the distances between targets, with an L2 distance in the tangent space. So the blue ones are exactly the same, but the red one is approximated now with this red distance, which is the LOT distance. And is very useful in many applications, in particular in machine learning. It's very useful to have metrics because we want to compare distributions. And in this simple, very simple image, I have 3 signals that are exactly the same, but they are shifted. So if I measure discrepancies with the L2 norm, notice that the L2 norm between blue and yellow is going to be exactly the same as blue and red. So there is, even though these 3 are different because they are shifted, there is no difference if I measure the pair distance with the L2 norm. So this creates problem when we use methods that involve gradient descent and etc. But the Wasserstein distance do distinguish these 3 pairs of measures, because moving Earth from the blue to the yellow is going to be cheaper than moving from blue to red. We have to transport more, we have to walk more distance from blue to red than from blue to yellow. However, the L2 norm is, we are more familiar with the L2 norm and not that much with the Wasserstein distance. So the LOT distance is in between these 2 distances, between these 2 metrics. So the LOT distance is an L2 norm, but in the embedded space, in the tangent space, in this new linear space. So in this space is an L2, but at the same time is a distance between probabilities. And the advantage with respect to the Wasserstein distance is that now we are picking a reference, and we are using that reference as a pivot. So if we have a lot of measures to compare, to do pairwise comparisons, then in case we want to compare them by using the Wasserstein distance, we will have to have n choose 2 optimal transport problem. We have to solve like n square optimization problems to compute the Wasserstein distance. But now with the embedding, with the LOT transform, we have to solve just n optimization problems because we have to compare all the news, all the new with the reference in order to obtain the hat, and then just compute an L2 norm between them. And the optimization problem that comes from optimal transport is very expensive. So by using this pre-processing tool, we are reducing the amount of optimal transport optimization problems. Okay. So to add on top of that, here the C comes from the thing that I want to introduce next, but the new distance that I'm introducing is an L2 distance in the tangent space, in the embedded space, that preserves to some extent the structures and properties of the Wasserstein distance. And in higher dimensions, computing this new distance is cheaper than the Wasserstein distance. I'm saying in higher dimension because in dimension 1, these two tools are the same. We have an isometry. And but also, since this is an L2 distance, we can pre-process our data, our measure, our signals with the transform, then embed them into an Euclidean space, the tangent space, the L2, and there use all the standard and classic method that we have there that are already like optimized. So there we can use the L2, the classical L2 norm as a functional to distinguish distribution, etc. Okay. So to convey that point, specifically the word that preserves the structure of the Wasserstein, I want to introduce some applications by using the circular optimal transport. So instead of working in Rn, I'm going to work in the circle, and the theory here is very similar to the theory in R. So my reference for all my examples, my reference measure is going to be the blue one, the uniform distribution on the circle. And then I'm going to pick any distribution on the circle, which I represent here with the orange color. And to do optimal transport, just the classic optimal transport, there exists a way of cutting and unroll this distribution to the line. And in the case of having the first one to be the uniform distribution, the cut has a closed formula. Is the antipodal point to the mean of the target distribution mu. So we know how to unroll, and here we have to match the blue to the red curve by using the theory of optimal transport. And in the line, we have a closed formula for doing that. Okay. And so let's do some experiments. So I'm going to start with 3 different classes of signals. My first class of signals are represented in green here. So I have a signal in dark green, and then I have all the translation of that signal. My second class of measure is going to be the blue one. Here I start with 2 bumps. That is my first signal, and then I shift I shift these 2 bumps to the right and to the left. And then the third class here is, sorry, I don't know if it is easy to visualize, and I think I have another question, but I start with the first bump, that is the one that I have here, and then I'm going to deformate this bump into the two bumps that I have here. So the guys that I have in the middle are like, okay, first I have like this mountain, then I have those two mountains, and etc. until I reach this last step. And I don't know if I can, sorry. Okay, and the question is, what do you actually do for computations? So for computations, in here that I'm going to use just probabilities in the real line. I have a closed formula for the optimal transport. So I pre-process all my data with the transport transform. So I compute a bunch of optimal transport having a closed formula, and then I use an L2 norm. That is for our tool. For also, you could have measures or data that are represented by point clouds. So they are for the matching, you use the, for the usual matching, you use the linear programming. And sometimes there is not going to exist a map. So our tool is not going to be well defined. So instead of using that, you use barycenters. So that is how actually we compute, but I'm not going to talk about that. My examples are going to be on the line, let's say, or circular distributions. Okay, and I'm trying to clean this here. Okay. And with these drawings, so I have the three classes of signals, and I'm going to embed them so that the distances are the same. So I have three plots here, because in the first plot, I'm going to do pairwise distances with our tool, the linear circular optimal transport distance. Here I'm going to use the circular optimal transport, the Wasserstein on the circle. And here I'm going to use the Euclidean distance between densities. So notice that, and here I have the pairwise distances in the embedded space with the multidimensional scaling embedding. So I don't know if I'm explaining clearly, but the distance here between these two dots is exactly the LCOT distance, the linear circular optimal distance between the density, this density and this density. So each point here is a density that I have here, but it's represented here as a point. And the distance between them are exactly the ones computed with our tool, with Wasserstein, with the Euclidean distance. So with the Euclidean distance, there is no cluster. The Euclidean distance cannot distinguish the three classes. The Wasserstein does. I have the big circle here given by these distances. So notice that moving from this to this is smaller than from this to the next one. Sorry, that's why these are like shifted in a circular way, because then these are like rolled up. And same happens here. These are the pairwise distances with the Wasserstein. And in this class, we move from one class to the next one, and here is the Wasserstein encoded that exactly. And this structure is preserved with our tool that goes to the tangent space. Okay, so that's the first thing that I wanted to illustrate with a toy example. The second application is image retrieval. So I have a data set of, here is also a toy example. Our data sets were a little bit small, like 100 of images of flowers. And I have a query image, and I want, and I represent all my images as the color scheme of them. So that's why I'm going to use a circular distribution. So each image is represented with a circular distribution of colors, the colors that I use to paint this image. And I'm going to retrieve the 4 closest images to the query image by using our distance and the Wasserstein distance. So the ones that I have on top, these 4 are the closest by using the linear optimal transport distance. And the one that I have below are the 4 further images by using the LOT distance. And the same below, but using the Wasserstein distance. So the first 4, which are pretty similar to what we obtained with our tool, are the closest in the sense of Wasserstein. And the last 4 are the ones that are further away from my query image by using Wasserstein. And the last application is interpolation. Oops. Okay. So I mentioned before 2 ways of interpolating measures by using like the trivial interpolation between 2 densities and by using the dynamic formulation and transport. So now we can use the trivial interpolation, but in the embedding space. So I'm going to use a line between my embedded signals, and then I'm going to go back to my original space, but by pushing forward that, by pushing forward with that curve of signals now of functions, by pushing my reference measure. So notice that in the embedding space, we use the naive interpolation as in the linear one. And then we have a way of going back because we have an inverse transform. So we can use the push forward to go back to the original space, to the space of measures. So we are going to use this and the interpolation by using optimal transport in order to in-paint. So I start with 2 images, this one and this one. So this is my source, my target. And I'm going to use the color scheme, the color palette of this image that has a lot of red in order to interpolate the color palette that I have here. So notice that here, when I move forward in time, this image becomes more and more red. So, and here I switch the role. So this is my original signal or color palette, and this is my target. So this image goes to more like bluish or greenish colors. These 2 are done by using our linearization, and these 2 interpolations with the optimal transport interpolation. Okay, so I think I'm more or less done with the time. I have like 5 minutes left. I've been like watching, but I lost my watch at certain point. Just to be very briefly, other things that we've been doing is trying to get rid of this, that we have to normalize every signal in order to have probabilities. So in order to get rid of that balance constraint, we have to deal with unbalanced optimal transport. So you start with two densities that might have different masses. So in order to set up the unbalanced optimal transport problem, if you start with the continuity equation, you have to add a source term. So then you have different minimization problems with that new term, and that you can also formulate in the sense of Kantorovich. But now your plan doesn't have to have marginals equals to mu and nu, but less or equal than those ones. So you are going to, I'm going to be a little bit, you are going to transport some parts, but some others are going to be destroyed and create. So suppose we have here a mu and a nu, and this will be the match with optimal transport. But you might have the case where these two points are outliers, in fact. So you don't want to match them. You prefer to destroy and create, and just match the part that is important. So that's why we want to introduce like the partial optimal transport, because this outlier could be noise or outliers in your sampling process. So the interpolation, when introducing that penalization, in case of having one part that is transported through a map, is going to be as before, and then you are going to interpolate the parts that you create and you destroy. And well, this is the work we've been doing that. And for this formulation, we also have a linearization, but this linearization here, the tangent space is not clear, so we don't have that mathematical structure from like math. So in our embedding, we have to keep track not only of the velocity of the transportation part, but also we have to keep track of how much mass we are transporting and how much mass we are creating. And by using this embedding, we can formulate a distance that resembles the distance of partial optimal transport, and do interpolation, and so on and so forth. So with that, I stop here. In order, if you have more questions, and I'm very, very thankful for the space, and thank you very much for your attention.
Thanks a lot. I will stop the recording now.